Oh, okay. Good. Okay, welcome everyone. It's my great pleasure to introduce Brendan Hassett from Providence, and Brendan will speak about rationality of an even-dimensional complete intersection of two real quadrics.
Okay, well, thank you very much. So it's great to see all of you, at least virtually. So this lecture actually originated from another talk I gave. I think it may have been in the Niaskovsky seminar, where I got questions from Janos about things. And so we discussed them. And so maybe I'm looking forward to this being a catalyst for future research. And so let me just get started with some background. Okay, so throughout we'll work over a field of characteristic 0, and I'm going to consider X a complete intersection of two quadrics, and it's always going to be here a smooth complete intersection. So so we're not going to consider really any singular examples. With defining equations F0 and F1. And so one important invariant is we look at the quadratic forms that contain X that are singular. And so this is given by the determinant of the associated symmetric matrices. So I'm taking here linear combinations of our defining quadratic forms. And I'm just saying, well, which linear combinations have vanishing determinant? And that gives you a homogeneous polynomial in S0 and S1 of degree d plus 3. And I'm going to call this the degeneracy locus of the family. So this is an important invariant that actually determines X over an algebraically closed field up to isomorphism. And so for each element in the degeneracy locus, I'm going to look at the associated singular quadric hypersurface, Q of S. And so, so Q of S is just one of the singular elements of the pencil. And one classical result here is that when the rank drops, it only drops by 1. That is, that the rank is equal to d plus 2 rather than d plus 1. And that is just an artifact of the singularities. And so again, these elements QS, these are singular quadrics in a linear series defining X. Okay. So let me just review some results over algebraically closed fields. I think many of you know this already. And so the basic construction is if I have an algebraically closed field, and if the dimension is not 1, so I need to have that the dimension is at least 1, then the variety of lines, the lines in the Grassmannian actually contained an X. This is non-empty. And moreover, projection from a line inside of X induces a birational map from X to the appropriate projective space. And so this proves that X is rational here under these circumstances. And so I'll take this as a sort of the basic easy rationality construction over algebraically closed fields. And to some extent, we'd like to explore whether there are other rationality constructions that are not just obtained by this projection construction. Okay. And so let me review a little bit of what is known in small dimensional cases. So again, we're going to let K be an arbitrary field of characteristic 0. And of course, in order to have rationality, you have to have a rational point. So this is necessary. Let me just make for rationality. You need to have rational points in order to have the X is rational over a field K. And so this is true in all dimensions. For surfaces, the work of Enriquez and Manin and Askovsky and probably many other people too give a pretty comprehensive characterization for rationality in terms of essentially the minimal model program for surfaces. So you need to have a point, but you also need to have that the surface is not minimal in order for it to be rational. So you need to have a collection of disjoint lines defined over the ground field in order to obtain rationality. And the geometry of the lines, the structure of these lines is quite important. So there are 16 lines altogether in the surface case. And they have a pretty intricate structure that I could spend a lot of time talking about, but I'll actually defer this until a little bit later where I can put things in a more general context. So the understanding the action of the Galois group on these 16 lines is important in assessing whether it's rational over a non-closed field. So this is a very classical picture. For three-folds, there's been some interesting recent developments. And so Benoit Wittenberg and also Schinkel and myself have developed a criteria for rationality in the three-dimensional case. And so X is rational if and only if it contains a line defined over the ground field. And so in some sense, this is saying that the easy construction that I indicated at the outset is really the only rationality construction that's available. And so Kuznetsov and Prokhorov have sort of expanded this line of investigation to cover quite a large collection of classes of geometrically rational three-folds. I'm not going to review much about what we and Benoit Wittenberg do, except to say that the intermediate Jacobian plays an important role. In some sense, the Clemens-Griffiths philosophy that the intermediate Jacobian should control rationality of three-folds, there are versions of this over non-closed fields. And this can be used to give necessary and sufficient conditions for rationality in good situations like complete intersections of two quadrics. And so there are extensions of this to fields of arbitrary characteristic, again for three-folds. The Benoit Wittenberg approach covers those cases. And so this is so this is a pretty nice circumstance. There's still some open, interesting questions for three-folds, but I'm not going to dwell on this too much. And so a question, which is in some sense originated from a throwaway, ill-considered remark I made in the talk, is in higher dimensions, can you be rational without containing any lines? And so I think I said this without really thinking too much about it, and pretty soon regretted it because I got lots of interesting suggestions of constructions that do this. So maybe I should just eliminate some of the drama here and say, so can it be rational without containing lines? And the answer is yes. And we'll discuss a little bit what those constructions look like. Okay, let me pause. Are there any questions or comments? Okay, then I will continue. So what I'd like to focus on now is some classification schemes for complete intersections of quadrics. And so, so these two classification schemes, they have somewhat different flavor. And I think the interplay between these is actually quite important, at least in my understanding of this. Probably many of you know these classification schemes at least as well as I do. But in my efforts to understand how they're connected with each other was an important part of this project. So two classification schemes, I probably should say. and how they're related. And so these are different ways of getting important Galois theoretic information from complete intersections of two quadrics. Okay. And so the first approach I'd like to talk about goes back at least to Miles Reed in his 1972 thesis. I think it probably goes back much further than that, but Reed's thesis is a really beautiful source of the information that I need, and so I find myself relying on it quite a lot. And so I want to emphasize here that the dimension of our X is even, just because the cohomological structure is more complex in the odd dimensional case. There is some weight one cohomology that I'm not going to dwell on here. So let's pass to the complex field for the moment. So let's embed our field into the complex numbers, and let's consider X as a complex manifold so that we can do Hodge theory. All of the cohomology of this complex manifold is represented by algebraic cycles. All the cohomology is of Hodge type. So the cohomology is only in even dimensions and is generated by algebraic cycles. And I'd like to fix a hyperplane class of X and look at the primitive cohomology, the orthogonal complement of the hyperplane class. And I'm going to do something slightly wonky here. I'm going to kind of change the signs here by applying this Tate twist. Basically, I'm going to do this because I really want these to be to have a uniform sign. And if I'm lucky, the sign is positive, definite here. So I know that for a quartic Del-Petzel surface, a complete intersection of two quadrics in P4, the natural sign on the intersection pairing is negative definite by the Hodge index theorem. So I'm really just switching the signs to shift the weight from 2 to 0 so that the intersection form is positive definite uniformly in all these even dimensions. So it's basically just to make my life easier from a notational perspective. So I have this primitive cohomology, and the primitive cohomology carries a lattice structure. And so the lattice structure comes from the intersection pairing on middle cohomology. And the resulting lattice, lambda, is actually isomorphic to the root lattice for the root system of type d to the 2n plus 3. And the associated weight lattice is given by looking at the sort of the saturation, the image of the full integral cohomology modulo the hyperplane class. And so n-dimensional subvarieties of X, like lines on a quartic Del-Petzel surface, they yield weights in this lattice. So I want to use this basic formalism for the intersection theory. And so let me just be pretty explicit in terms of the structure here. So if you have a basis E1 through E2n plus 3 for a Euclidean lattice with a standard diagonalizable intersection pairing, I can think of the dn root lattice as being given by the differences between successive generators. In addition, I take the sum of the final two generators, and I describe pretty explicitly what the weight lattice is. And the reason why I'm getting into the details of the basis elements is to be able to describe the Weil group in this context. The Weil group, it can be realized as sign permutation matrices with an even number of -1s. And so they're permutation matrices with respect to this Euclidean basis that I've specified here. And so I'm using this notation so as to make it easy for you to understand what the possible symmetries are of the lattices. And these symmetries will reflect possible symmetries of the underlying manifolds. And so here I wrote down, just for my sanity, the D5 intersection matrix. I hopefully did it correctly. This is, so if I did it correctly, then this should be the intersection matrix associated with the root system. Of this kind. So I think this is 1, 2, 3, 4, 5. So, so we're going to think of the cohomology of our complete intersections as carrying this structure, because it gives us a way of understanding the possible Galois symmetries. And so if you remember, I talked about the 16 lines. So just remember that the symmetries here, they govern the symmetries of the 16 lines. On our complete intersection of two quadrics in P4. Okay. So let me say a bit about the dictionary here. So the weights of the standard representation, the standard representation meaning, the representation of the standard representation of the orthogonal group. So the Dn root system corresponds to representations of an even dimensional orthogonal group. And so the weights of the standard representation of the orthogonal group. So in this identification, they correspond to the images of quadric n-folds, Q and X, that arise from maximal isotropic subspaces of these singular quadric hypersurfaces I described before. So if you remember, there were 2n+3 singular quadric hypersurfaces. So we saw at the beginning that the degeneracy locus has 2n+3 points. And each of these quadric hypersurfaces, it has even rank. And that means that there are two different types of maximal isotropic subspaces. And those give you the plus and minus EJs in the root system. And so if you want to realize the roots of the standard representation in terms of the geometry, they just correspond to the quadric n-folds. An example, of course, is in a quartic del Pezzo surface. These are the conic bundles on the quartic del Pezzo surface. So maybe I'll just write a note here. So for n equals 1, these are the conic fibrations. For X and P4. And so the weights of the spin representation, they correspond to either n planes or their residual intersections, which are kind of like twisted cubics or Segre threefolds, or what you get when you intersect a plane by an appropriate linear subspace. So it's to get something residual of the same dimension. And so these correspond to the weights of the spin representation. So for example, in the D5 case, so the spin, we get 16 lines. And so they correspond to the weights of one of these spin representations. So anyway, I want to draw out this connection to help clarify what are the natural sort of indigenous symmetries that are associated with these varieties and their cohomology. And so the last thing I want to point out is that when we're working over R, so we want to keep track of the various degenerate quadratic hypersurfaces that contain our complete intersection. And so I can interpret complex conjugation. This corresponds to an involution in the root system. And these are characterized by triples of numbers read off in the block decomposition of the corresponding representatives. And so this is a way of getting kind of a topological invariant of a real complete intersection of even dimension just by recording these numbers. And so these are maybe the most obvious invariants, at least from a representation theoretic perspective. So these just come from looking at conjugacy classes of the Weil group. And so again, we're looking at involutions that are sign permutations, and up to conjugacy, they're all of the form +1, +1, +1, -1, -1, -1, and a whole bunch of these 2x2 blocks here. And so this gives you invariance of the conjugacy classes of involutions in the Weil group. Okay, I think this is what I would like to say about the sort of the Reed perspective on the classification. So now let me go to a different perspective. Are there any questions or comments before I switch? Let me just look at the chat. Okay, let me press on. So another really beautiful approach, the isotopy problem, is I learned about it in Krasnov's papers. So part of a larger program to understand real connected components of real smooth projective varieties. And so let me say a little bit about this now. So this is, so again, X is given as a complete intersection of these two quadrics. And we have the degeneracy locus that comes from the determinant. And then we base change to get a family of fibers over the circle. And so the way I'm thinking about this, maybe a little bit strangely, is I'm thinking of S1 as mapping to P1 of R in the standard 2-to-1 antipodal map, so that I identify opposite points. And the only reason to do this is so that the number of positive and negative eigenvalues of the corresponding quadratic forms, that this is well defined once I do this base change. Without doing a base change, I get confused about signs, and so I would like to keep track of the signs. And so the number of positive and negative eigenvalues, it is unchanged as you restrict yourselves to smooth fibers in the family, but there are transition points when you approach points in the discriminant. And so let me kind of draw a picture here of how I think about this. So I have S1, and then I have some distinguished points here. And so these are the elements, the real points of DR. And then there are complex conjugate imaginary points of DR that I'm not showing up here, that to some extent remain in the background for this classification. All right, so now as you transition from one side of a point on the discriminant to the other side, the signatures could either increase or decrease. And in fact, if I kind of, maybe I should do this in a way that makes clear the antipodal structure. So I didn't draw this quite correctly, but let's say that these two are antipodal elements and these two are antipodal elements. And so for the antipodal pairs of points lying over some point in the discriminant, the signature increases at one and decreases at the other. And so we kind of keep track of what happens to the signatures as we go around. So maybe in this diagram here, we might have signatures like this. So maybe here we have a signature 3, 2, and then I cross and transition, and the signature goes to 2, 3. And then I cross again, and it goes back to 3, 2. And then I cross again, it goes back to 2, 3. So as you make the transitions across the singular fibers, the signature of the quadratic forms changes. And so we record that information as we go around the circle and a counterclockwise orientation. All right, so then we record as we go around S1, and we keep track of sequences as signatures go up and down. And so maybe I'll show you how the bookkeeping goes. So in this example here, I guess I have to remember to go counterclockwise. So here we're going minus, plus, minus, plus. So I just keep track of how the signatures change as I go around in the diagram. And so we get a sequence of changes. Wait a second here. All right, let me undo that. I think I made a mistake there. All right, let me actually go from the example here that I take. So as we go through, we get a sequence of sign changes. So pluses and minuses. And the key thing I want to emphasize here is that antipodal points, they have opposite sign changes. So here's the first ones. So these have opposite sign changes. Or this and this have opposite sign changes. And so I get a length of sign changes, twice the cardinality of the real points of the discriminant. And so this basically tells you how things vary over the circle. And then we record these in this sequence of numbers, 3, 3, 1. And so the 3, 3, 1, they correspond to, well, so I have, let's see. So I have these 3 elements here. And so let's say it corresponds to this. And these 3 elements here corresponds to this. And then I have what's left over. So I'm basically just keeping track of these transitions in as we go across the points in the discriminant. And so the invariant here is a sequence of positive integers, R1 through R2s plus 1. It has to be an odd number of such integers. And so this is a well-defined up to cyclic permutations and reversals. And it satisfies these following conditions: that the sum is at most d plus 3, the number of degenerate fibers, and that the sum is also congruent to d plus 3 modulo 2. And so this is what we're going to call the Krasnov invariant. And so Krasnov shows that this is a complete invariant of the isotopic class for complete intersections of 2 quadrats. If we just keep track of how the signatures vary, we get a complete invariant of real complete intersections of quadrats. So for odd D, we allow the empty sequence as well. Okay. So now we have these 2 different ways of thinking about the classification of real quadrats. So we have the Krasnov invariant. And so let me just emphasize again, this Krasnov invariant. So this is a complete invariant. And then we have the, maybe I should call this the Weil or the Reed invariant. I'm not sure what we get from looking at the corresponding involutions in the Weil group associated with complex conjugation. And so we get those invariants. And the general approach is that I can go from the Krasnov invariants to get the Wall invariants, but it could be the case that two Krasnov invariants, they give you the same Wall invariant. And so you can see this in one example here, where we get two different isotopy classes that give rise to the same conjugation in the Wall group. So the Krasnov classes associated with the given Wall class, they can be interpreted as kind of shuffles. I fix the number of plus and minus signs, and then I just shuffle them in a way that's compatible with the antipodal condition. And so I found these numbers in the online encyclopedia of integer sequences. So it grows pretty quickly. Well, there's only one example in this case, but as the dimensions get larger, there can be quite a lot of shuffles involved. And so there can be very large numbers of Krasnov isotopy classes associated with a given conjugacy class of involution in the Wall group. So let me just reiterate that these are here. These are conjugacy classes of involutions in the Wall group. Okay, so we have these different invariants. The one reason why I really like the Reed approach is that, let me just make this clear. One reason why I really like them is that I find the dictionary here to be quite important. That is, there's a pretty clear connection between the structure of these Wall groups and the structure of the degenerate quadric hypersurfaces containing our complete intersection. And I just find it easier to make the translations between the invariants and the geometry working through the Wall group. It helps me to organize the information. So, so the Krasnov machinery is very powerful, but I think to see the implications for these degenerate quadrics that contain X, it's helpful to understand the structure of the Wall group as well. Okay. So I think I'm done with the classification side. Are there any questions or comments? Okay, then I will press on. So let me talk a bit about the rationality results here. And so basically, the theme of the talk is rationality results over R, but with reference to our classification schemes. So we'll talk a little bit about the implicit assumptions here. The implicit assumption that I'm making is, in some sense, rationality should actually behave well under these isotopy classes. And so we'll come back to that assumption in a moment. But this is, well, when your only tool is a hammer, everything looks like a nail. So I'm going to focus on what I can say that is uniform across the various classification schemes for isotopy classes. Okay. So, so let's see. So results on irrationality. Let me start with that. So let's say that we have, again, a smooth complete intersection of two quadrics over R. And the first thing I want to emphasize is that there are no rational points precisely when the Krasnov invariant is D plus 3. And what this basically means is here is that all possible signatures arise, right? So if it's D plus 3, then you go from positive definite to negative definite. And so that includes the definite form. Now, if you have a complete intersection of two quadrics, and you know it can be embedded in a positive definite quadratic form, well, the positive definite quadratic form, right? These definite Q's, these have no real points. So if I can put X inside the definite quadratic form, it's not going to have any real points either. And so the point of this classification is that that's really the only thing that can obstruct the existence of real points in these complete intersections of two quadrics. That is, there are no real points precisely when X can be embedded in a definite quadratic form, definite quadratic hypersurface of dimension D plus 1. So, all right, so this is the first step. The second step is that there's a characterization for when XR is disconnected in terms of the Krasnov invariant. And so that is given here. So when it's has a very large number, but not quite as large as what we saw before. So if it's D plus 1, 1, 1. So in this case, the locus is non-empty, but disconnected. And so it's not so hard to see, certainly in small dimensions, why this is the case. For example, you could have an elliptic curve in P3 that's a complete intersection of two quadrics. And the real points there, you can see pretty clearly that they can be disconnected. You can have two distinct ovals. And so those are classified in terms of Krasnov invariant. So if you have something like this, where I have an intersection of a sphere, and then, I don't know, maybe a hyperboloid. I'm not going to draw the other hyperboloid, but so that the induced curve looks something like this. So, so these are the non-empty disconnected cases. And there's one distinguished case in each dimension. And I should mention is that this explicitly, so if X is rational over R, it must be the case that XR is connected. Because in real birational geometry, the connected components are in fact a birational invariant. And so these are the cases, these are the irrationality results. So these statements here. When there are no real points, or when the real points are disconnected, you get irrational examples. All right, so this is one extreme. So, so where you have the irrationality results because of the essentially topological structure of the real points. On the other hand, we have the quote unquote easy rationality construction. So where there are lines. And so these are characterized as follows. And so the Amer-Brumaire theorem, which tells you that a complete intersection of quadrics has a point if and only if the corresponding family of quadrics has a section, or a complete intersection of quadrics has an isotropic subspace, if and only if the corresponding quadric vibration has a similar isotropic subspace. We can use the Amar-Brumaire theorem to show that the only isotopic classes, other than these two topologically problematic ones, are given in this classification here. And so there's a very small number of possible Krasnov invariants that might not have lines. And so this observation proves rationality in almost all the Krasnov classes, except for the short list. So let me just emphasize here. So all the other classes are rational. From the existence of a line. And so we really want to focus on these last sort of difficult cases that don't have lines. Okay. So are there any questions about this slide or about the approach? That is, we want to exclude the things that are obviously not rational, and we want to sort of label the things that are clearly rational for general reasons, and focus the attention on what's left. All right, so now I'm going to do that. And so we're going to focus on the cases that aren't covered. And so let's talk about the first case when you have conjugate degenerate fibers. So this is a case 2n plus 1. So another way of thinking about this is that we're assuming that so D has two imaginary points. But otherwise, we get the full range of different signatures. All right, so here's the statement. So let's assume that we have a complete intersection of two quadrics over R with the Krasnov invariant 2n plus 1. Then X is in fact rational. And so here's a construction. We go through and we translate the Krasnov invariant into the structure of these quadric n-folds. So if you remember, I spent a fair amount of time developing this kind of dictionary between what we know in terms of the classifications and what we know in terms of various middle dimensional subvarieties. And so we pick a quadric n-fold associated with one of the imaginary points in the degeneracy locus. And then we take its complex conjugate. And in typical situations, these two quadrics, they intersect in exactly one point topologically. And since Q intersected Q bar is conjugation invariant, this point is actually a point that's defined over R. So we get a distinguished real point where these intersect each other. And then projecting from that real point, we get a cubic hypersurface. When I project from a point on a complete intersection of two quadrics, I get a cubic hypersurface, next lower dimension. And the images of our quadrics become disjoint planes. And if you have a cubic hypersurface with two disjoint planes, so let me try to draw this schematically. So here I have Y. And then I have these two disjoint subspaces. These are complex conjugate, but well, let me not draw them as such. Then the classical three-point construction, where I take the points on these lines and join them, and then look at the residual point of intersection. This third point construction, it gives you a map from the restriction of scalars, Pn, from C to R. And so this is here. This restriction of scalars is in fact rational. To our cubic, to our cubic hypersurface and P2n plus 1. And so this gives us a rationality in this case. So this is the first example where you have a rationality construction, but you don't have necessarily a line defined over the ground field. Indeed, the fact that you have this Krasnov invariant precludes the existence of a line. You can see this just by looking at the specific fibers that they don't contain one-dimensional. The quadric hypersurfaces containing X, they don't contain the requisite isotropic subspaces. Okay, so this addresses the first case that that was left out. So here I'm looking at so let's see. So I guess this case, at least in the even dimensional situation, is resolved. Okay, I'm gonna go on to the next. Are there any questions before I go on to the next case? Okay, let me proceed. So here is the next Krasnov invariant where we're assuming that we have two equal large sequences of uniform signs. And so let's say that we have a complete intersection of two quadrics with that invariant. Then X is also rational. And so now we again use the dictionary from the Krasnov classification to the Reed classification to get information about distinguished subvarieties in X. And so the construction is as follows. So suppose that we have a quadric n-fold that's defined over the ground field. And we have another n-fold T that has a property that when I intersect it, the intersection with the sort of residual subspaces is odd. And so then what happens here is we get a picture that looks like this. So I have a base So I have a base Pn, and then I have all these quadric fibers. So this is a projection from Q. This is projection from Q. And now I have this distinguished residual subvariety T. And I'm going to assume that this defines some multisection, draw it like this, of this vibration of odd degree. So the key thing here is that this quantity is odd. And so that translates into saying is that this T has odd degree over the base. Well, if I have a quadric vibration with a rational multisection of odd degree, it will actually have a section. So the existence of a rational section, this is generally known as Springer's theorem. And so the Springer theorem will give us a section of this vibration. Well, let me draw it here. But if you have a quadric hypersurface vibration with a section, then it's rational over the base. And since the base is projected space, it's rational over the ground field. And so all that you need to do is to show that when you're in the situation of the Krasnov classification, you have the requisite quadric n-folds, because you have two quadric n-folds that have the desired intersection properties. And if you work back through the Krasnov classification and the reclassification and do the bookkeeping of what you have, what the isotropic subspaces of the fibers give you, you can show that you actually have the requisite n-folds inside of X. And so that completes the case n plus 1, n plus 1, and 1. All right. Any questions about construction 2? Check that. So the last case is when I have 3 terms, one of which is 1, and then I have the E, this kind of undetermined entry is equal to an even number. And here they're rational as well. And now the construction is a bit different. If you remember at the beginning, I told you exactly which combination of weights are in bijective correspondence with the n planes. And so using this dictionary, I can keep track in terms of the Krasnov classification, which conjugate classes have disjoint conjugate n planes. So, in which cases you have a plane P and a plane P conjugate that don't meet each other. Now, when you have that, it's a good situation because I can essentially repeat the argument that I did 2 slides previously and get a cubic hypersurface in P2n plus 1 with disjoint linear subspaces of half the dimension. And the rationality construction applies again. So I'm basically repeating what I showed you and this earlier slide using the 3-point construction and restriction of scalars. And so the presence of these disjoint planes, they also allow you to prove rationality in these cases. All right, so these are pretty elementary constructions. So you're all so skillful in birational geometry. These and the level of sophistication are probably like a 2 or 3 and a level of 1 through 10. But I just wanted to show you what you can see more or less immediately from the classification using the the dictionary in Reed's thesis. So let's kind of review what we've obtained here. So here's the summary. So in dimension 4, a smooth complete intersection of 2 quadrics is rational provided the set of real points is connected and non-empty, if and only if. So I probably should have emphasized here. This is in fact an if and only if. So if the real points are connected and non-empty, then it's rational over R. So in dimension 6, we don't have a complete picture. So if it's complete, if the real points are connected and non-empty, then we know it's rational over R in all cases, except when it's in the isotopic class associated with the Krasnov invariant 531. And so this case of 531 is a one open case in dimension 6 that we do not know how to address. Okay. So we have a complete picture in dimension 4, and we know most of what's going on in dimension 6. Okay, I'm running a little bit low on time. So let me engage in a little bit of a speculation. So what could the construction be when you have a Krasnov invariant 531? And so here's a possibility, just based on sort of squinting at the cohomology and looking at which cycle classes seem to represent varieties defined over the reals. So one possibility is that from the intersection theories is that an X with invariant 5 through 1 contains what's called an edge optic, which I have to confess I did not know anything about until I started this project. But there's a really beautiful paper of Chiliberto, Mella, and Russo, and another work by Russo, where they discuss exactly what kinds of special subvarieties force cubic hypersurfaces to be rational. And the edge optic is one of those subvarieties. It's basically constructed from a vector bundle, stable rank 2 vector bundle on P2 with these Chern classes. Here, L is a hyperplane class. And when you look at the global sections of the bundle, it gives you a realization of the corresponding threefold, the projective P1 bundle over P2 as a subvariety of P7 of degree 8. And so it's known that if V contains a cubic, then a Y has to be rational. And so we can speculate whether there's a way of producing these edge varieties just based on where X sits in the isotopy classification. I don't know the answer to this, but in terms of the cohomological invariance that we can compute readily, there's no obvious obstruction to this. And so this raises a lot of questions. If you have cohomology classes over R and it looks like they support certain kinds of subvarieties, how hard is it to actually produce those subvarieties? So this gives a hard proof of rationality for certain examples in dimension 4, where instead of taking the edge optic, one takes a quartic scroll. However, this hard proof of rationality does not apply in as many cases as the easy proof that I presented to you. And so let me just raise a more general question. And so this is kind of like the unspoken assumption here. This is the unspoken assumption that underlined everything that we did today. And so that is rationality and isotopy invariant at all? That is, let's say you have a family of complex varieties, and let's say that they're smooth projective varieties over some moduli space, and that they're all rational over the complex numbers. And so do we know whether the rationality is controlled by the isotopy class? Now, my suspicion is probably not, but I don't know an example where you have uniform rationality over C and rationality isn't determined by isotopy type invariance. Probably one of you will just come up with an example in real time, and I'll burn these slides so that they're never seen again. But I don't know an example off the top of my head. And so in some sense, right, the philosophy underlying this talk is that looking at isotopy of the real points is a sensible tool for trying to understand rationality properties. But that assumption is not really very well supported, at least not supported at higher dimensions. I guess I should say, so Janos, my apologies, this is okay for surfaces. But that's basically because the rationality properties is determined by sort of the structures of the lines. Yeah, so I mean, it's a general question: to what extent over R is isotopy a reasonable notion for organizing rationality, provided that all the varieties involved are rational with the complex numbers? So I am last minute, and I have one slide, and so let me engage in some less speculations over other fields. So let's take a more general field. Over finite fields, these questions are relatively straightforward, just because we have results of Lang, and I know that control when the varieties of lines have points, and so these are not so interesting. There are similar results, at least in dimensions 4 and higher, over complex function fields, but I don't know much about p-adic fields. And so what if we have X defined over a p-adic field, and let's just assume that well, we don't want to assume that it's a good reduction, because then we can reduce the finite field case. But let's assume that the Galois representation is at least unramified. What can we say? So in some sense, it would be really nice to have a Krasnov style classification over local fields, at least in cases where there's not complicated wild ramification that you have to keep track of. Anyway, this is kind of speculative, but I hope that some of the work that we did to sort of understand the isotopic classification using the language of the Boyle group, whether that might actually pay some dividends when we pass to more general fields than the reals. All right, thanks a lot. Happy to answer any questions if there are any.
Thank you, Brendan, for beautiful talk. Thanks, Brendan. And in Zoom. Okay. Okay, questions, please. Any questions?
Brendan, do you have a complete classification of when the real points are connected? Your condition wasn't an if and only if, was that?
Yes, it is actually an if and only if. The only case where they're disconnected. Sorry, I did not write that more clearly. Yeah, so here, yeah, so this I should have said that this is if and only if. That's the only case where it's disconnected and not empty.
Any other question?
How about stable rationality?
That's a really great question, and I don't know much about it. Yeah, I don't know. It would be beautiful to have an instance of these complete intersections of two quadratics that are stably rational, but not rational. Yeah, excellent question. I wish I knew the answer to it. I don't know that the kind of resistant cases, you know, the 5-3-1 case that I alluded to, I don't have a proof of stable rationality in this case. I haven't really thought about it very closely, but yeah, I think that's a really good point. Whether you could use this as a testing ground to produce new examples of stably rational, non-rational varieties.
Another naive question would be, I mean, you said what happens for finite fields, but what about other characteristic P?
Yeah, I never got past the finite field case. Let's see. For a function field of a curve over the algebraic closure of a finite field, a version of the Graeber-Harris star theorem should probably apply. I think, well, but now that I think about it, do we know that the varieties of lines are separably rationally connected? Probably generically, yes. Yeah, so even in that case, I think that there'd be some work involved, because my expectation is that de Jong's characteristic P version of the Graeber-Harris star theorem should get you something, but it generally is difficult to specify which of a hypersurfaces or families of zero loci for sections of vector bundles when they're separably rationally connected in a family. That's kind of a hard question, I think, in general. And there's lots of vexing counterexamples in Janosch's book that, you have to be thoughtful and careful about these things. So I would guess that would be true, but maybe the separable rational connectivity would be a bit of a bottleneck. So I guess I'm saying, I don't know. And it'd be nice to have a kind of a more hands-on approach that doesn't rely on the machinery that's a little bit indeterminate in concrete examples.
Any other questions? Okay, if no other questions, thanks, Brendan, again.
Yeah, thanks for having me. It's a
Thank
pleasure.
you. It was great talk. Let me stop recording. Okay.